Hello friends, welcome to this new videos of this lecture series. This is the lecture number 6. In this lecture, I will cover mostly the hold constraint, which is the one of the important constraint in STA. And in the next lecture, I'll try to cover the mathematical expression of the hold time constraint. Just as a brief, I want to tell you that in last 4-5 lecture, I tried to cover mostly the basic timing concept and definition, and then the STA constraint, which is a setup constraint. And in this video, I will try to cover the whole constraint. So mainly the things is that here also we have a two type of definition of the whole time constraint. I'm coming into that, but as you know that everywhere we use this type of sequential circuit of small sequential circuit, which is a part of a big one. There the two flop is connected in series with a in between there is a combinational circuit. And I'll come why I'm saying this is a this is a buffer insertion, and maybe there is a delta delay. I will come into that, but the whole time is mainly that suppose you want to sample your data in a particular clock age. Suppose you want to sample your data in a particular clock age. Maybe this clock age is actually we are talking about capture flip-flop at this point. In setup time, what I am talking about? I am talking about mostly this type of time that there would be a small amount of time there would be a small amount of time will be there to set the data before coming at the particular clock age. But in whole time also, before any changes into the data should also valid after some time. The data should also valid after some time at the proper particular clock age. Okay. So this is the whole things as a setup and hold window. And this is a very basic definition. In this definition, you will not understand how the hold violation is actually working. So to understand the hold violation actually it's working, let's understand that why I am talking about this delta. Suppose this is this is your C2 clock path and this is your C1 clock path, and because there is a buffer insertion in that C2 clock path, obviously whatever the clock signal is coming from the source generator, that clock signal will reach delta nanosecond delay after delay at this clock sync point. So that same thing I represented here, that sorry, there is a change, that this is 0 clock flop 0 and this is a clock flop 1. So why this is a delay? This delay actually representing your delta nanosecond delay. And because of that what is happening actually at flop q at a flop 0 at the flop 0 at the q0 point, whatever the data I am saying, that maybe this is the input data ABCD, this data is coming from this way, this data is capturing at any particular clock edge. Suppose this any particular clock edge. Okay, but because of that this delta delay, because of that buffer insertion at flip-flop capture flip-flop, at the capture flip-flop, or you can say the next flip-flop, the data also capture at the same edge of at the capture flip-flop output also capture the flip-flop 0 at the same edge due to that small delay. So the problem actually is whatever the flip-flop 1's clock is only slightly delay, it still triggers on the same clock edge as flip-flop 0. What I am saying, that because of that flop 1, clock is only slightly delay, it still triggers on the same clock edge as flop 0. So it means that both flop 0 and flop, you can say flop 1, that launch and capture flop, both captured same data at the same clock edge. That is the problem of double clocking actually. So I tried here to give you the essence with input sequence with the clock waveform. So what it mean that in the same clock edge that P is sampled. Maybe in that next clock edge A is sampled, but what will happen? A can sampled also at the same clock edge. B is sampled here, but B is sampled at same clock edge. Okay, this is the problem actually. So I think you understand the two basic definition of hold constraint. Same thing I written here in a sentence that so that you can understand very well. It violates our assumption that data launched by the flop 0 will captured by the flop 1 after one full clock cycle. This is our assumption. We need that because same things we discussed in the setup time constraint also, that whatever the data we are launching from that launch flop, by the next clock edge or after the one full clock cycle, the data should be sampled at the capture flop. But what is happening here? Happening is main the double clocking. The double clocking is the problem. The double clocking is what is the problem? The data captured by the two flops by the same clock edge. So this is a problem of multiple capture of the same data. That's the same thing I am showing here. The same thing I am showing here. So our violation is created from that double clocking violation. Whatever the double clocking things is happening, we have to avoid this, and that is actually the hold violation we want to avoid. Okay, so same thing I written here. I don't want to again read that. You can read here. The next thing is very simple. Like maybe till now you will understand a little bit of the hold constant, I hope that. But I tried to take an example, and by that example maybe you will understand very well that how we can represent in a waveform with a number, numerical number. Okay, here what I represented, what I showing here, same thing, that two proper D flop, flop 1 and flop 2, and in between C2 path, clock path or capture clock path have a delay of 1 nanosecond, and there is a clock to Q delay is 2 nanosecond, and there is a combinational delay of 2 nanosecond, and here also a 2 nanosecond of propagation delay. And I want to know about the setup time and hold time. That d0 point whatever the data is coming is constant, that one data. Okay, so our main things is, you can very easily understand, this is the clock we are accepting at this point, and this is the clock we are accepting at this point. Okay, and because of why there is a delay of 1 nanosecond, because of that clock to Q delay of 2 nanosecond, the Q0 will be like this much. Because of that clock to Q delay of 2 nanosecond, so your data is kind of this much. I think you understand already. This much your 2 nanosecond data delay. That is a combinational delay of 2 nanosecond. So that's why I'm adding extra 2 nanosecond in that. You understand? So here I'm saying that this is the delay of 2 nanosecond and this is the total delay of, this is the delay of 2 nanosecond, this is the delay of total delay of 4 nanosecond. Then I need my data to proper sampled at this point. It is the Q0, sorry, it is the Q2, this is the Q1 and this is the D2. Now I think you understand very well. This is a Q1 data. After 2 nanosecond, after 4 nanosecond, there is a D2 data, this point data, and Q2 should properly sampled by the next clock edge. As we know that our main takeaway is this much amount of time you will get as a setup window. And how much it is, we will calculate, we can calculate by the setup equation. And this much amount of time you are getting as a hold. But there is a catch. There is a catch. You can say this much amount of time is a hold. You can say that my hold is something is less than equal to 4 nanosecond. But your hold time is getting worse. Because why? Because this clock edge and this clock edge is not exactly at the same point. Because there is a 1 nanosecond delay, your hold constraint is getting something called 3 nanosecond. Why? Because 4 nanosecond is a actual D2 delay up to D2 point, and there is a 1 nanosecond delay of this. So your hold constraint is getting worse. So there is a chance that the data which you are sending from this point can be sampled at the same clock edge at this point. So that's why we should everywhere talking about the hold constant. Mostly we talked about the hold constant when we do the clock tree synthesis. When we do the logical STA, we rarely talking about the hold time constant, but when clock tree synthesis and sign off stages, that time we talk about the hold time constant. I tried to cover very two basic definition of hold time constant. One is by this clockage and another how the double clocking things is happen. And with one example, I tried to evaluate that how the setup window and hold window is actually working with a timing waveform. Thank you for listening this video with your patience. Thank you.